Howdy, my name is Nicholas Starvaggi. I'm a second-year PhD student in Dr. Emily Penzo's group at Texas A&M University, and today I'm going to be demonstrating the use of the Horiba Partica LA960 for particle size analysis.
The Horiba Partica LA960 here at the Materials Characterization Facility operates via static light scattering, also known as laser diffraction. This technique is commonly used in physical chemistry to measure the intensity of scattered light as a function of scattering angle. Rather than measuring particle size directly, as you can see in the figure, laser diffraction measures the angle and intensity of the light scattered from the particles in the sample. This data is passed on to an algorithm which uses Mie scattering theory, transforming the scattered light into a particle size distribution. Importantly, static light scattering can be used to obtain much more than particle size. One of the most common applications is the determination of the weight average molecular weight, M sub W, of macromolecules such as polymers, proteins, or viruses. This technique can also be used to determine the radius of gyration, R sub G, or the form and structure factors. Finally, the measurement range for this instrument is 10 nanometers to 5,000 microns. Depending on the method selected, a user will need as little as 10 milligrams or as much as 5 grams of sample. Finally, a typical measurement takes about 60 seconds, again dependent on the method selected, from liquid filling, sampling, and measuring to rinsing.
There are three general methods for measuring particle size analysis using this instrument. The first is the dry cell method, in which a dry sample, about a tablespoon, is placed into this top trough here, and then the sample falls into the instrument through this long, narrow trough and moves into the instrument. So from the trough, the sample falls through this cylinder and then down into this window through the path of the laser, at which point a measurement can be collected. Now the second method is the liquid cell method, in which case the sample is dispersed in water, at which point it comes down this hose into the window, once again into the path of the laser for a measurement to be collected. Now the third method is the fraction cell method, and this is in the case if the user doesn't want the solvent to be water, you can fill this fraction cell with a solvent of choice, whether that's isopropanol or acetonitrile, really whatever the particles are compatible with. And again, this window is placed in the path of the laser, allowing a measurement to be collected. One of the interesting features about this instrument is that the cassette is removable. So when placing it back into the instrument, depending on the method that you're using, whether it's the dry cell, the liquid cell, or the fraction cell, you'll align the arrow with the path of the laser inside of the instrument. So the method that I'm going to be demonstrating today is the fraction cell method. So once the cassette is inside of the instrument and aligned with the red arrow, you're going to want to make sure that the other connections for the other cells are out of the way so that the path of the laser remains free. So that means connecting up some of the hoses and wires that might be associated with some of the other methods of collection. So the sample that we're going to be measuring today are microcapsules of ionic liquid with a polyurea shell. So I've placed about 50 milligrams of the capsules into this vial. At this point, we can go ahead and disperse them gently in about a milliliter of methanol, like so. And you can see that the capsules, after they sit for a while, they tend to aggregate a little bit. So we can go ahead and sonicate them very briefly, just about 5 seconds, in order to break up some of the clumps. Based on optical microscopy and SEM, we know that these microcapsules should be on the micron scale, somewhere between 10 and 80 microns in size. And now we'll use the fraction cell method to obtain a much more precise particle size distribution. So I've removed the fraction cell from the instrument, and the first thing you're going to want to make sure of is that the interior and the exterior of the cell are clean. So the interior, the last user should have flushed the window with isopropanol just to make sure that any residual impurities have been completely removed from the system. And for the outside, because the laser has to pass through the window, you're going to want to make sure that there's no smudges or fingerprints on the window itself, and you can do this by just gently cleaning the outside of the glass with a Kim wipe, like so. Next, you're going to want to go ahead and fill the fraction cell with the solvent of choice, in this case methanol, and place it back into the instrument to collect a blank measurement. This is the software that the instrument uses to measure particle size. I've already loaded the refractive indices for the sample, which has a polyurea exterior, and the solvent, which in this case is methanol. The next step is to align the instrument under preparation, and then collect a blank measurement. So the next step is to go ahead and load our sample into the fraction cell. So we begin by taking just a small aliquot of our sample and just gently place it inside of the fraction cell. And at this point, you can go ahead and agitate the mixture a little bit because some of the particles will settle out faster than others. This is just to ensure that a nice even measurement can be collected by the instrument. Now that the sample has been loaded, we can go ahead and shut the door and move over to the measurement screen. Now the most important thing to consider is this blue transmittance bar, and you want to make sure that that bar is within the window that's provided. If the bar is above the upper limit, it means that there's not enough sample in the fraction cell. However, if the bar is below the lower limit, it means that there's too much sample in the fraction cell, and you either need to remove some or add some solvent to dilute. Now the next step is to go ahead and click Measure to collect your particle size distribution.
All right, let's take a look at the data. At the end of each measurement, the instrument generates the following report, which contains the particle size distribution and some key data points. The user can choose to replot the data using a third-party software, such as Origin, or simply copy the graph as formatted by the system. Of note, this instrument provides a mean size and respective standard deviation, geometric mean size and respective geometric standard deviation, and mode size, as well as listing the selected parameters and refractive indices. Today, I completed particle size analysis on microcapsules of ionic liquid. The sample was produced through an emulsion-based template, which is known to have little control over particle size. Thus, a relatively broad distribution and high standard deviation, as shown, is expected for this sample. However, if the user were to measure, for example, monodispersed nanoparticles with a standard size, a much narrower size distribution would be observed.
So now that we've collected a measurement, the final step is to clean up. So we can go ahead and remove the fraction cell from the instrument, pour the contents into this glass beaker, like so. And to prepare it for the next user, we're going to go ahead and want to clean out the inside with isopropanol. We dispose of that like so. And then we can go ahead and dry it using this pressurized air. And then again, wiping the outsides with a Kim wipe just to ensure that it's ready for the next user. That about wraps it up for this tutorial. In conclusion, if you plan to use this instrument or a different system for particle size analysis, make sure to consult the provided guidelines, as standard operating procedures may vary from instrument to instrument. Thanks, and Gego.